Let's resume. In the previous video, we talked about comparison test, and then we talked about this limit computation, this integral problem 2.5, and we use comparison test kind of like this in straightforward fashion. E to the negative x power function is positive, so throw that away. Then what we have, we just reduced my function kind of like this. An even smaller function diverges if you take the integral, as this computation shows. Consequently, the bigger function must generate infinity as well by comparison test. It works out great. Now let's move on to the second problem, and it may not be as simple because, well, okay. Alright, we got something like this, which means this should be finite. I don't know what the heck that is, but it is finite. Maybe numerically calculate. Yes, it is finite. But how do we justify that? Well, let's begin with this estimation. This is less than or equal to this function because I just reduced the denominator, consequently making the function bigger. But then again, what do I do now? The numerator is still complicated. If I throw away this one, then I'm going to end up making the function smaller. So the comparison test does not work. I have to get something bigger than this, or at least equal to this, and calculate the integral. But if I raise and then reduce, I'm going to lose control. How do I handle that? One way to handle that is to do this. It's rather unconventional, but we can do something like this. What did I click? We can decompose the numerator kind of like this. And then the first function is 1 over x to the 7/2 power. And the second function is x to the 1/2 7/2 power minus 2, so 3/2 power. And they both have p-value greater than 1, so they'll both generate finite integral. Let me show you. After this computation, take the integral, then this integral and this function and that function will both generate finite value. So we have finite integral. Consequently, even smaller function will generate finite value as well. And that's how the comparison test works. It's difficult, isn't it? We got something simple, yes, but then again, this decomposition, Another way to handle that is this one. The first solution, 1 plus x squared is less than or equal to 2x squared when x is sufficiently large, greater than 2. And then work out from here, and then we have 2 over x to the 3/2 power. P-value is greater than 1, so we have finite integral. Consequently, the original integral must be finite as well. Works out, but again, this is not easy. This estimation over here, just getting 2x squared, is kind of out of nowhere, kind of difficult. Just as difficult as this decomposition. Is there any better way to? In fact, there is. Intuitively speaking, instead of working out the inequality, which are hard to work with and they are strict, let's work out asymptotically. Because when x is really, really big, like some gazillion, adding 1 will not make too much difference. So throw that away in denominator and also numerator as well. Then what do we have? We have a power function, x to the 2nd power, over x to the 7/2 power. Consequently, we have x to the 3/2 power. This time p-value is greater than 1. We can clearly see that we're going to get a convergent integral. But then again, do we have any justification for that? It seems it is working asymptotically, but is that true? The answer is yes. We don't have to work out the inequalities precisely. We can get away with approximation as long as we do appropriate justification. That justification is called limit comparison test. When f and g are positive functions, then take the limit of the ratio. If the limit is neither 0 nor infinity, then the integrals must behave pretty much the same way, asymptotically. If one converges, then the other converges too. If one goes to infinity, the other goes to infinity as well. If you use that, then this kind of asymptotic estimation is fully justified. Kind of like this. We take that, and then we already have it here. And then we're going to take this to denominator, and then original function goes to numerator, and then calculate this limit. Well, this is a limit computation, so you can throw away those ones, and after some simplification, this plus 1, that plus 1, or any lower order power, just throw them away. As a matter of fact, why do I have square root of x here? It should be 1. Anyway, we have limit value 1, which is neither 0 nor infinity. Therefore, two improper integrals behave the same. The p-value is greater than 1, so it converges. Consequently, the original one also converges. This method is very, very powerful. It's a little bit cumbersome in that you have to do the limit computation, but if your function is far more complicated, then this kind of method works like a charm. And we have really complicated function, but as long as they're all algebraic, and consequently we can find out the growth order by taking the highest order terms and throwing away the rest for both numerator and denominator, then we can find out the growth order estimation by this asymptotic computation. And then what do you do next? Justify it with those limit computation of the ratio. However, this method is a little bit advanced, and then at this moment it may look a little bit difficult. So our textbook author decided not to talk about this one for some time. Basically, he decided to tiptoe into this estimation business, and at this moment he is just showing you those comparison tests, and full-blown limit comparison tests will show up in chapter 11. So here we go. You can stick to those comparison tests and then use those for variety of situation, including the kind of situation it doesn't work very well with some ingenious techniques like decomposing the numerator, kind of like that. Or you can study limit comparison tests a little bit ahead of the schedule. The choice is yours. I talked about both, and you can choose whatever method you like to. In the end, you have to learn both, because in chapter 11 they both come back in full power. Okay, looks like we are pretty much done except for the last problem, so let's talk about it. Find the a value that makes the following improper integral converge, and evaluate the integral for that a value. The last part will turn out to be a little bit cumbersome. Let's go. One way to handle that is by brute force, calculate the indefinite integral of this thing, and then, well, you'll see, calculate the indefinite integral, and that will not turn out to be so simple, to tell the truth. Consequently, we have to work out something that I'm not gonna diverge for a moment, and then you have to find out appropriate condition for a, where this expression converges. And let me just show you the answer briefly. It's long, very long like this, and this is actually a condensed version. If you sit down and write everything, it's going to be even longer. Calculating the antiderivative is not too bad, but you're going to end up with two logarithmic functions. Somehow working out with those two will turn out to be challenging. One way to handle that is that, but now that we talked about limit comparison tests, let's talk about a shortcut. Here it is. Let's take the common denominator of the integrand and then do some brute force computation. Take the common denominator, numerator turns like this, and then break up the parentheses and then put those coefficients together. Then what we have, the coefficient of the highest order term of the numerator turns out to be 3 minus a, and denominator has growth order extra third power. So in terms of asymptotic estimation, we have 3 minus a x squared over 3x cubed. As long as this 3 minus a is not 0, in that case, you'll have to go over to, well, next order, because x squared term will disappear. As long as 3 minus a is not 0, as long as a is not equals to 3, this will generate x squared over x cubed, so we're going to get growth order of 1 over x. By limit comparison test, we're going to have divergence. So here's my conclusion. As long as x is not equal to 3, we get a growth order of 1 over x. P-value is 1, so that's going to diverge. This original integral will diverge. So we have rather simple solution like this. Just brute force computation and putting those, comparing the coefficient, we get the condition a has to be equal to 3 to have any kind of chance. Go over to the next stage here, next step here. When x is equal to 3, when a is equal to 3, then this x squared term will disappear. So what do we have? We have growth order of 1 over x squared. We'll have convergence. The problem is, when a is equal to 3, what is the integral? And that computation will turn out to be a little bit of challenge, but not impossible. If you run Mathematica, then you have this kind of solution. But how do you actually get that? The detail is left to the students.